In this video, we're going to talk about quadratic functions. Now, ultimately, our goal is to get to polynomial functions, but we're going to explore quadratic functions because it will be an easier way to expand to polynomial functions. We can know quite a bit of information already about quadratic functions. Okay, before we do that, let's do an example that uses quadratic functions that we will find why it's going to be useful. We're about to kind of look at. We're actually going to come back to this example later, but let's talk about it first. So backyard farmer wants to enclose a rectangular space for a new garden. She's purchased 80 feet of wiring fencing to enclose 3 sides and will put the 4th side against the backyard fence. So there's already an existing fence that she's going to use. Find a formula for the area enclosed by the fence if the sides are perpendicular to the existing fence have length L. So the perpendicular comment is so that we know that this is definitely a rectangle here. Okay, so we're working with a rectangle. And since they're asking us to find a formula for the area, we know that the area of a rectangle is length times width. But they don't formula in terms of length and width. They want it just in terms of length. So here's what we're going to do. I know the other piece of information they gave us was that she has 80 feet of fencing that she's going to use. So that would mean that this fencing here, right, around this perimeter, that's going to be 80 feet total. So this happens to be length L as well, which means that L plus W plus L is going to equal 80, or 2L plus W equals 80. And if I just solve this for W, then I can plug this into my area equation and say that the area is going to equal L times 80 minus 2L, or another way of saying that would be 80L minus 2L squared. And they might even call this AL, in other words, finding the area based on length. The formula for the area. Now, we'll come back to this, but ultimately I'm interested in kind of exploring more about what this tells me. Okay, before we do that, let's focus in on some specific points of interest for quadratics. In particular, we are interested in the short run, they call it short run behavior. That's how our book refers to it. And we're interested in a major point called the vertex. So the vertex is that kind of turning point on the parabola. Okay, that point where it turns. So when we look at f of x equaling x squared, we know that that turning point right here, that's the vertex. Now, before we talk more about the vertex, we're going to kind of use a previous example from transformations, where we're going to figure out an equation for this based on x squared. Okay, so I see, based on where I know x squared is supposed to be, x squared is supposed to start at 0, 0. So this thing has shifted down 3 and left 2. All right, so that would mean then that the x squared, to go down 3, we would minus 3 from the whole thing. And to go left 2, that means I would add 2 to the x. So here's my potential new formula. However, it's possible that this thing is expanded or stretched, condensed or stretched vertically. So I might need to find that vertical compression or stretch, because it kind of looks like it might be squished, right? The normal parabola, let me do it in green like I did a second ago. The normal parabola goes through 0, 0, and then 1, 1. So it looks a little bit skinnier than what I'm seeing here. So I'm thinking they may have condensed this. So I need to figure out what A is. One way to do that is to plug another point in from the graph. So here, I'm going to pick a nice point. I'm going to pick the vertical intercept right there, 0, -1. So I'm going to plug in 0 for x and -1 for y. So y in this case is g of x. and then x is going to be 0. And what that leaves me with is a, the only variable I don't know. This potential condensing. I'm sorry. Wow, why do I keep saying condensing? This potential compressing of the graph, compressing factor. Okay, so here, let me solve for a. So that's going to be 2 squared, which is 4. And then here, I'm going to add 3 to both sides. So that's going to give me 2. And that's a 4a. So a is 1/2. Right? When I divide by 4, a is 1/2. So that means an equation for this would be g of x equals 1/2 x plus 2 squared minus 3. Now, I want to connect this to the vertex. And that vertex, like I said, is the turning point on the graph. I see that the vertex occurs at the ordered pair -2, -3. All right, so let's connect that to the equation we just had right here. I see a -3 right there. I don't see a -2. I do, however, know that because the graph shifted left 2, that 2 right there occurs because of the fact that it shifted left 2. It's like relocating the vertex of the original graph. So that connects directly to a parabola or a quadratic formula. So let me write this out then. In standard form, a standard form for a quadratic means that we are looking at it as f of x equals, oh, sorry, I'm sorry. They want the standard form for this quadratic. So a standard form means I'm going to multiply it out. I'm not going to have it with that squared. Sorry, I didn't read it carefully. So I'm going to multiply this out. I'm going to actually multiply x plus 2 times x plus 2. That's what x plus 2 squared is. And then I'll multiply it by 1/2 and minus 3. Okay, x plus 2 times x plus 2 is, okay, distributing and FOIL, same difference. Okay, so that's going to be x squared plus 2x plus 2x plus 4. So that's going to be x squared plus 4x plus 4, which I'm going to multiply by 1/2. Not pleasant, but I can handle it. And I still have this minus 3. Okay, so multiplying by 1/2. Here, I'm going to kind of come up over here just because of space on mine. So that's going to be 1/2 x squared. 1/2 times 4 actually works out nicely. That's a 2x plus 2 and then minus 3. Okay, so the final then would be g of x equals 1/2 x squared plus 2x. And then the 2 and the minus 3 combined to be -1. So this would be that same equation in standard form. So standard form means that we have it multiplied out. So this standard form, the general standard form for any quadratic is ax squared plus bx plus c. And you may have seen that in a previous class before. In fact, I tend to teach it this way when I start doing factoring. Okay. If it is in transformation form, like how we saw it when we wrote our example up here with the parentheses, here's how that is written. That is in this form, f of x equals a, same a, by the way, as the a up in the standard form, x minus h squared plus k, where h and k happen to be the vertex. This is also called vertex form. In fact, this is called vertex form more than it's called transformation form. Vertex form is kind of that standard way of referring to where we can see the vertex in the equation itself. All right. To actually find the vertex of a parabola from the equation, there is a formula for that. The book develops this formula, and I encourage you, if you'd like, to go find it. It is h equals -b over 2a. That's referring to the standard form. So if it's in standard form, we can find the vertex by doing negative b over 2a. And then to find the k value, you would simply plug h into the formula. Or in other words, find what negative b over 2a is when we plug it in for the x. All right, let's try it. So let's take this quadratic, which is in standard form, and put it into vertex form. So I'm going to find the vertex. I'm going to find h. So this would be a, this would be b, and this would be c. So the b happens to be negative. So this is going to be a negative 6, because the formula has a negative there. So negative 6 over 2 times a, which is 2. So it's going to be negative. Oh, sorry, here. The 2 negatives become positive. So it's going to become, which reduces to 3/2. So that is the x coordinate of the vertex. So to find the y coordinate, the k, I'm going to plug 3/2 in for x. So 2 times 3/2 squared minus 6 times 3/2 plus 7. And I encourage you, if you haven't learned how to do fractions on your calculator, learn how to do fractions on your calculator. That's going to make your life a little bit easier in plugging this in. But here, if I'm going to work it out all the way, this is going to be 9/4, because that's 3 times 3, 2 times 2. Let's see. This I could think of as 6 over 1, which means I'd have 18/2 or 9. Okay, so this is going to be 18 over 4, which reduces to, sorry, lost my train of thought there. 18 over 4, and 18 over 4 actually, oh, sorry, here. Let me go ahead and add the 9 and the 7. So that's going to be negative 2. 18 over 4 actually reduces to 9/2 minus 2. If I want to get a common denominator, then that would be 4 over 2, which is 5/2. All right, great. That's doing all the work by hand. Don't do the work by hand. If you don't know how to do fractions on your calculator, maybe send me an email. Then we can Zoom together and I could show you how to do fractions on your specific calculator. All right. But just figure out how to plug into your calculator if you don't want to do it by hand. So that's the vertex, 3/2 and 5/2. This quadratic then in vertex form would be written as f of x equals 2. So the same a value, x minus 3/2 squared plus 5/2. And notice it's a minus because the formula is a minus. See, minus h. All right, so the other way of finding the vertex is using completing the square. If you didn't know the vertex formula, and I know you kind of feel like, well, why would I do that if I know the vertex formula? The answer is you probably won't. However, this particular method that I'm going to show you in this example is something that's used in calculus. So anybody moving into calculus, it's going to be valuable for you to see the process I'm about to do for that later on. Okay, so if I want to find the vertex by completing the square, this is how you would do it. So it's probably been a while since you've done completing the square. The way completing the square works is the first number, the a value, we need to actually have it be a 1. So I'm going to start by factoring out 2. Now, often when we complete the square, we move the c term to the other side. So actually, I was thinking about before factoring out the 2. You could minus 14 and bring it to the other side to where the f of x is, so that you're left with 2x squared minus 12x. Then you would factor out 2. And this is what I want to complete the square on, this right here. That's what I want to complete the square on. Oops. So I have this f of x minus 14 over here. And I want to complete the square on this quadratic that's in the parentheses. So the way you do that is you take half of -6 and square it. So half of -6 is -3. -3 squared is 9. So I'm going to add 9 to that quadratic. But I'm not allowed to just add things, okay? I have to add it to the other side as well. So I'm going to add 9 over here as well. However, I'm technically not adding just a 9. I'm actually adding 9 times 2. There's a 2 in the front there. So I actually need to add 18 to the other side. Okay, so here's what I got. I got an f of x. And then that 18 and the -14, that's going to combine to be a 4. Okay, times this. So the point of this is that this now factors into a perfect square, x minus 3 squared. And now I can move that or re-isolate f of x. I can move that 4 back over to the other side. And now it's in vertex form. So the vertex for this is 3, -4. That's the vertex for this quadratic. And I see that from this. So if you don't remember how to do completing the square, I could probably post one of my completing the square videos just to kind of review that process. But it is a little bit altered because I'm not solving an equation. I have this f of x here and it's kind of messing with things. So I have to alter it by factoring that 2 instead, and then moving the 14 to where the f of x is and just leaving the f of x there. So it's a little clunky, but this is how you would complete the square to find the vertex form. Okay, so let's move on then. What this is going to allow us to do, what we just discussed here, is actually going to allow us to talk about our first example when we talked about the backyard farmer creating a garden. All right. So let's come back to this example. And what this is going to do is this is going to help us find a maximum or minimum value for the quadratic. So when we look at a quadratic, there's really only 2 choices. Either it faces upward and the vertex represents a low point, or it faces downward and the vertex represents a high point. So that means that we're going to be looking at either a maximum or a minimum value when we look at the vertex. So coming back to our example earlier where we created our area formula, A of L equals 80L minus 2L squared. That was our formula that we came up with. I can tell this is a quadratic because it's an L squared, right? So let me put it in the right form. Let me put it in descending order. So I'll put the -2L squared first plus 80L. Okay, so this is my A, E, and then C in this case would be 0, right? Since there is no C. Okay. So this is a quadratic and it's a downward facing quadratic because of the negative in the front, which means it's going to have this kind of scenario where it's got a maximum point. And since they're asking me to find the dimensions that's going to maximize the garden, what they're asking me to find is the vertex. So that's what I'm going to do. I'm going to find the vertex. So the maximum is going to occur at the vertex. So I'm going to find it. So H equals -b, which is -80 over 2 times A, which is in this case. So -80 over -2, that comes out to 20, right? Because that's -80 divided by -4, which is +20. All right, so if I take 20 and I plug that into the original equation, I can find the k value, the vertex for the k value. And that's going to be A of 20, which is -2 times 20 squared plus 80 times, oops, sorry, there's a 0 next to that. 80 times 20. So let's see, that's going to come out to I'm like running out of space here. 800. All right, so there's our H and K. So in vertex form, really quick, I'll just take a second, write it in vertex form. This is going to be, oh, here, let me go actually off of this version where the A is first. So this is going to be -2 times L minus 20 squared plus 800. Okay, so here's what's exciting about this. This 20 is the value that L is going to be. That's my L value, the length that's going to give me the largest maximized area. And the actual largest area is, in fact, 800. That's what this represents. So the maximum area is going to occur when L is 20. I don't remember what the measurement was. I think it was feet, 20 feet, which means that the maximum area is going to happen. It's going to be 800 feet squared. Now, the width, by the way, which we found previously, is going to be 80 minus 2L. So 80 minus 2 times 20, which is 40, and 80 minus 40 is 40, so 40. So 20 feet by 40 feet is going to give us a maximum area of 800 feet squared. And we'll talk about intercepts in the next video.